And welcome back as we continue our journey looking at stars. We, of course, previously looked at the brightness of stars, but now let's go ahead and discuss how we can look at the different colors of stars. So to start this off, let's go ahead and take a view of the Sagittarius star cloud. And in this, we can see a bunch of stars here. This image actually shows us the stars that are in the direction toward the center of the Milky Way galaxy. Now, these bright stars glitter kind of like colored jewels on a black velvet background. Now, the color of a star is indicating its temperature. So, blue-white stars are much hotter than that of our own sun, whereas red stars tend to be much cooler. And of course, we have a kind of spectrum of colors in between. So, how can we relate color and temperature besides just a very basic rule? Well, Wien's law actually relates stellar color to that of stellar temperature. Blue colors, and by that extension ultraviolet, dominate the visible light output of very hot stars. Cooler stars emit most of their visible light at red wavelengths and at the infrared spectrum. So the color of a star therefore provides a measure of its intrinsic or true surface temperature. Color does not depend on the distance to an object. It doesn't matter if we're close up or far away. And if we could somehow take a star, observe it, and then move it much farther away, its apparent brightness or magnitude would change. But this change in brightness is the same for all wavelengths, and so its color would ultimately remain the same. Now, star colors do have a correspondence with their approximate temperatures. So the hottest stars have temperatures of over 40,000 Kelvin, and the coolest stars have temperatures about 2,000 Kelvin. Our sun's surface temperature is about 6,000 Kelvin. Its peak wavelength color is a slightly greenish yellow. Now, in space, the sun would look white, shining with about equal amounts of reddish and bluish wavelengths of light. Now, the reason why we typically make our sun more yellow is because when we look at the sun from Earth's surface, our planet's nitrogen molecules scatter some of these shorter wavelengths. And to really put into context just what colors kind of correspond to temperatures, if we were to look at, for example, stars that are blue in color, we typically say those are much hotter, where they have approximate temperature about 25,000. An example of this would be Spica. White stars are going to be about 10,000 Kelvin. Example of this is the star Vega. Yellow stars is around 6,000 Kelvin. Again, that's our own sun. Orange stars are about 4,000 Kelvin. So Aldebaran is an example of that. And for red stars, we have about 3,000 Kelvin. And Betelgeuse is, of course, going to be our representative of that category. Now, the color indices, of course, are important when we are looking at stars, because if we want to specify the exact color of a star, astronomers normally measure a star's apparent brightness through various filters, each of which transmits only the light from a particular narrow band of wavelengths. Now, one commonly used set of filters in astronomy measures the stellar brightness at 3 different wavelengths. U for ultraviolet, B for blue, or V for visual, or what we like to think of as yellow. Now, these filters transmit light near the wavelengths of 360 nanometers, 420 nanometers, and 540 nanometers, respectively. Now, the brightness measured through each filter is usually expressed, therefore, in magnitudes. Now, the difference between any of these two magnitudes is what we refer to then as the color index. Now, the ultraviolet, blue, and visual magnitudes of the UBV system are adjusted to give a color index of 0 to a star with a surface temperature of about 10,000 Kelvin, such as Vega. The BV color indexes of stars range from about negative 0.4 for the bluest stars, with temperatures of about 40,000 Kelvin, to about positive 2.0 for the reddest stars, with temperature about 2,000 Kelvin. Now, the BV index for the sun is about plus 0.65, and you'll note that this index is always the bluer stars minus the redder stars color. So, one of the things you might wonder is, why do we use a color index if it ultimately implies temperature? Well, that's because the brightness of a star through a filter is what astronomers measure, and we are always more comfortable when our statements have measurable quantities. Because anytime you can verify it with actual data rather than simply just assumptions, it is, of course, something that you can test and verify.